Hi, in this video we are going to talk about space complexity of algorithms or programs. Space complexity is defined as order of growth of memory space or RAM space in terms of input size. It's similar to time complexity. Time complexity is order of growth of time taken of an algorithm or program in terms of input size. Instead of time taken, here we have memory taken or RAM amount taken. Let's take a look at these two programs to get an idea. This program takes how much space in terms of input size? Only constant amount of space. You have some constant number of variables n. There is in fact only one variable n. So the amount of memory space does not grow in terms of input size. If you have n equal to 1000, then only you are going to have only one variable in this program n, right? And as long as the number of variables are constant, it's not an array of variables or array of memory. It's considered as constant when we talk about space complexity. Let's see this program. It's another way to find sum of first 10 natural numbers. It's a way to do direct formula and it's a way to add the numbers one by one. Can you guess the space complexity of this program? How many variables we need in terms of input n? Say if n is 1000, how many variables you need? Sum, I, right? And then 3 variables. And then if n is 10,000, then also you need 3 variables. Sum, I and n. So the space complexity of this program is also big O of 1 or theta of 1. Please note that we represent space complexity also using same asymptotic notations as we do for time complexity. So space complexity of these both programs is theta 1, or you can say big O1. They both represent constant order of growth. But we cannot use omega 1, right? Omega 1 means it's minimum constant, it might be higher. So theta 1 and big O1, they give proper information that it's always going to be constant, not more than that. Let us take a look at this function. In this function, we are receiving an array as an input, size of array as an input, and what we do, we run a loop to find sum of elements in the array, right? We traverse through all the array elements, do the sum and then return the sum. Now, what is the space complexity of this program? If you talk about input size n, if n is 1000, then how big your array is going to be? 1000 size. If n is 10,000, then your array is going to be of size 10,000. So the space complexity of this program is theta n. It's always going to need theta n space in terms of input size. The space grows linearly in terms of input size, and that's what is the exact growth. Right? It's not an upper bound or lower bound. We know exactly that it's going to grow theta n in terms of input size. So we use theta notation to represent the exact growth. Let us now define one more term, auxiliary space. This is the term we use most of the time. We use it more than space complexity. Auxiliary space is order of growth of extra space or temporary space that you create to solve a problem or to write a code for a given problem. If you take a look at this array sum function, what it does, it takes an input array, finds the sum of elements in the array. So space complexity of this program is clearly theta n. We have talked about it because the space required for this program, the RAM space required for this program is going to grow linearly in terms of input size. But if you talk about extra space, space created for memory other than input output, how much extra space this program needs? It needs linear space only for input. It does not use any extra array to do any computations. So auxiliary space for this program is theta 1, but the space complexity of this program is theta n. Auxiliary space theta 1, space complexity theta n. When we talk about array problems, or list problems or any problems which use an input container, they are anyways going to need theta n space. Their space complexity is going to be at least theta n. And if you use an array or an extra array of size n, the space complexity is going to remain theta n. So rather than space complexity, we care about auxiliary space. For example, when we study sorting algorithms, there are some sorting algorithms which do not use extra array to do the sorting, like insertion sort, bubble sort, selection sort. However, there exist sorting algorithms that use extra space to do the sorting, extra array to do the sorting. For example, merge sort. Merge sort is a sorting algorithm that uses an extra array of size n to sort an array. If you take a look at all the sorting algorithms, they are all theta n space complexity because they are all need an array to sort, right? But we cannot compare them in terms of space complexity because they are all theta n. So we compare them in terms of auxiliary space. How much auxiliary space a sorting algorithm requires? We say insertion sort, selection sort, bubble sort, heap sort, they are all theta 1 auxiliary space. Merge sort is theta n auxiliary space. Quick sort is theta log n auxiliary space in best case because quick sort has recursion. We'll talk about some recursion space complexities as well in this same video. So space complexity is less used and auxiliary space is more used because it gives you more information. So space complexity is a less used term compared to auxiliary space because if you're talking about array, list, you need space complexity theta n to process them. But you can compare algorithms by auxiliary space. You can decide which is better by taking a look at the auxiliary space they require. Let us take a look at this recursive program to find sum of first n natural numbers. How does this program work? It takes an input n. If n becomes 0 or less than 0, it returns 0 as sum of natural numbers. And if n is something positive, it adds n and calls for fun n minus 1. So how does this work? Fun 5 calls fun 4, fun 4 calls fun 3, fun 3 calls fun 2, fun 2 calls fun 1, and then fun 1 calls fun 0. Right? And what fun 0 returns? It returns 0 to its parent. Right? Then what parent does? It takes this 0 and adds to n. And what is n for the parent? Parent has n as 1. So it returns 1 plus 0, 1 to its parent. Then this returns n, which is 2 for this function call, 2 plus 1, 3 to its parent. And then it returns 3 plus 3, 6 to its parent. Then it returns 6 plus 4, 10 to its parent. And this function returns 10 plus 5, 15 to the caller. So we get the value 15 returned from this function call. So this is how this recursive function works to do sum of n natural numbers. Now what is the space complexity of this program or auxiliary space required for this program? If you take a look at this, you are not using any array or a list or any other data type like hash table or anything to store any extra variable. But this program does not have theta 1 space complexity or theta 1 auxiliary space. This program needs extra space. This program needs extra space to store these function calls in a function call stack. So how do these function calls work? You have fun5 initially in the function call stack. Then fun5 calls fun4. And fun5 is waiting here for fun4 to finish. Then only fun5 can resume. So fun5's state is stored in the function call stack. Then fun4's state is stored. Then fun3's function state is stored. And none of these functions can finish until fun0 has finished. Once fun0 finishes, it returns control back to the caller, then caller finishes, then caller of the caller finishes, then parent of it, then parent of it. So that's how these function calls happen. Now there is a movement when you have n plus 1 function call stacks, function calls states stored in the function call stack, right? At a movement, in the worst case, what will happen? Fun5 will be there in the function call stack when fun0 is called. This will happen when fun0 is being executed. You will have fun4, then you will have fun3, then you will have fun 2, then you will have fun 1, and then you will have fun 0. So you need to have space for 6 function calls. N plus 1 is the extra space required in the worst case. There is a moment when you have n plus 1 function calls stored in the function call stack, right? N plus 1 functions activation record stored in the function call stack. So the space complexity required for this program is theta n. N plus 1 can be written as theta n. And you can also say auxiliary space for this program is also theta n. Let us do an exercise considering different solutions of Fibonacci number. Let us find out space complexity and auxiliary space for all these solutions. The first solution that I am going to consider is simple recursive solution for Fibonacci numbers. Please pause this video, draw the recursion tree of Fibonacci numbers and try to guess the space complexity and auxiliary space for this program. They are going to be same for this. Before we talk about auxiliary space or space complexity, let me clarify the problem more, the solution more. So we are talking about Fibonacci numbers where nth Fibonacci number is defined as sum of n minus 1th Fibonacci number and n minus 2th Fibonacci number. This is 0th Fibonacci number for n equal to 0. This is for n equal to 1. We expect the output as 1. For n equal to 2, we simply do a sum of these two and we get 0 plus 1, 1. So this is for n equal to 2. For n equal to 3, we do a sum of recursive calls for Fibonacci 2 and Fibonacci 1 and we get 2. Right? That's what we are doing here. And we are handling the base cases. If n becomes 0 or 1, we return n. For 0, it's 0. For 1, it's 1. I have also drawn the recursion tree for Fibonacci numbers. Let's now understand the extra space this program is going to take. I just want to give you a simple formula to find out auxiliary space required for any recursion. It's always equal to the height of this tree, maximum length of root to leaf path. So you can see maximum length of root to leaf path here is 4, right? And that's what auxiliary space and space complexity is for Fibonacci numbers. And we can always find out this way. So we can say that auxiliary space required for n equal to 4 is of order 4, which means it grows linearly in terms of time. So that's a direct way to figure out. We can say that auxiliary space for required this recursive Fibonacci number is theta n. Let's now understand how I might define this formula that it's equal to the maximum height of recursion tree. What happens when you call it recursively? You call it for Fibonacci 4, and Fibonacci 4 begins its execution from here, comes here, and then makes a recursive call for Fibonacci 3, right? So what do you have in the recursion call stack as of now? You have Fibonacci 4, then Fibonacci 3 goes into the recursion call stack. So you are here, then you came here. Now Fibonacci 3 also begins its execution from here and comes to Fibonacci 2, right? Calls for Fibonacci 2. So Fibonacci 2 also goes into the recursion call stack. So you called for this as well. Now Fibonacci 2 again begins its execution, does not go into the base cases, calls for Fibonacci 1, right? So Fibonacci 1 also goes into the recursion call stack. Now Fibonacci 1, it begins its execution from here, goes into the base case and returns 1 immediately to the parent. So 1 is returned to the parent. And Fibonacci 1 has finished at this point. It does not make recursive calls. So Fibonacci 1 is done. It goes out of the recursion call stack. Now control goes back to Fibonacci 2, and what Fibonacci 2 does, it has already done with the Fibonacci 1. Now it calls for Fibonacci 0. So Fibonacci 0 goes into the recursion call stack. And you can notice that before Fibonacci 0 was called, all these height things of the recursion call, they were there in the recursion call stack. Now this path is there in the recursion call stack. So at any moment, the number of function calls you have in the recursion call stack is paths from root to leaves. So one moment you have these many function calls, then you have these many function calls, then you have these many function calls, then you have these many function calls, and then you have these many function calls. So Fibonacci 0 begins its execution, goes into the base case, and returns immediately, and it goes out of the recursion call stack as well. So Fibonacci 0 is not here now, and it returns 0 to its parent. And what parent call does? It does 1 plus 0, 1, and gives the control back to its parent. Now parent, which was waiting for here, now makes a recursive call for Fibonacci 1. So Fibonacci 1 begins its execution, it goes into the recursion call stack. Fibonacci 2 also goes out of the recursion call stack, right? Because Fibonacci 2 was finished when these two were called. Now Fibonacci 1 goes into the recursion call stack. Because Fibonacci 4 has made a call for the right side. So this is the new recursion tree path from root to a leaf. Now Fibonacci 1 finishes its execution because it's in the base case and returns the value 1 to its parent, right? So Fibonacci 1 goes out of the recursion call stack. Now parent also is done because fun 2 is over, fun 1 is over. And what does it return? It returns 1 plus 1, 2 to its parent. So for Fibonacci 3 also goes out of the recursion call stack. Then control comes to Fibonacci 4, which was waiting for Fibonacci 3 to finish. Fibonacci 3 has finished, and now it's going to call Fibonacci 2. And Fibonacci 2 is going to call Fibonacci 1. So you can see now you have the next path in the recursion call stack. Fibonacci 1 finishes its execution, goes into the base case, right? Returns 1 to the parent call. And then it calls, Fibonacci 2 calls Fibonacci 0. Fibonacci 0 also finishes. So Fibonacci 0 also goes into the recursion call stack before being finished, right? So you again have this path in the recursion call stack. And then Fibonacci 0 goes into the base case and finishes. Now the parent gets the control back, returns 1 plus 0, 1 to its parent. And this Fibonacci 4 returns 2 plus 1, 3 to the parent call. So we get 3 as an output. At any moment, we never required more than height of this recursion call stack space in memory. That's why we say auxiliary space or space complexity required for this program is theta n. Let us now take a look at another solution to find nth Fibonacci number. What I've done here is I've created an array of size n plus 1 and I call this array as f. For n equal to 4, I'll create an array of size 5 with indexes 0, 1, 2, 3, 4. And then I'm initializing the first two Fibonacci numbers as 0 and 1. So this is initialized as 0 and this is initialized as 1. Now I run a loop for I equal to 2 to I equal to n and I plus plus, and what do I do in this loop? I use the same recursive formula. So this becomes I minus 1 plus I minus 2, so it becomes 1. This becomes I minus 1 plus I minus 2, so it becomes 2. And this becomes 1 plus 2, 3. So that's how we compute the Fibonacci numbers now. And we return the result as 2, or return the result as 3. Now what do you say about space complexity and auxiliary space for this program? Please pause this video and try to guess the solution yourself. Both space complexity and auxiliary space are theta n here. We need n plus 1 space for this auxiliary space. See, we can always ignore the extra 1 or 2 or 3 or 100 constants, right? As long as they are constant number of constants. We only need to consider auxiliary space which grows in terms of input size, right? So this is the array which is dependent upon n, right? If n is 1000, this array is going to be size 1001. If n has 1 lakh, then it's going to be 1 lakh plus 1. So this array grows in terms of input size. So auxiliary space required for this program or this function is theta n. Same as space complexity. Space complexity is also theta n. Let us now take a look at this another solution to find the nth Fibonacci number. The idea here is to optimize the previous solution in terms of space. If we see the previous solution, to find the ith value in fi, we were only using fi minus 1 and fi minus 2. So instead of creating the whole array of size n, we can just store the previous two Fibonacci numbers in two variables, right? So I've created two variables a and b here, which store the previous two Fibonacci numbers, and I store the current Fibonacci number in C. Initially, a is 0 and b is 1. So let's do a dry run of this for n equal to 4. What happens? You do not go into the base cases, we have handled them explicitly. Then we come for I equal to 2 and we run this loop. What do? We make C equal to 0 plus 1. We make a equal to b. So a becomes 1 and b becomes 1. b is equal to c. So you can see that before going to the next two Fibonacci number, before computing the next Fibonacci number, we have the previous two Fibonacci numbers, right? A is 1 and b is 1. So next Fibonacci number can be easily computed as a plus b. That's what we do in the iteration for I equal to 3. Right? We make c equal to 2. And then we update a and b accordingly for the next iteration. We update a as b. So a has the second previous Fibonacci number for next iteration, and b has the previous Fibonacci number, right? So b is equal to c by the end of this loop, right? So when you begin next time, you have the previous two Fibonacci numbers here. Now you compute the current Fibonacci number, then you update the previous to previous Fibonacci number, then you update the previous Fibonacci number. That's how you get nth Fibonacci number at the end, and you return it. This particular solution, how much space it requires, how much auxiliary space, and what is the space complexity? You are only using a constant number of variables. A, B, C, I. Number of these variables is not dependent upon the n. The auxiliary space required is not dependent upon the n. So space complexity and auxiliary space both are theta 1 here. Both are theta 1 in this example. So we did in space optimization in the previous solution, and we got the solution which works in theta 1 space, and same time taken by the previous solution was also theta n, time taken by this solution is also theta n. In this video we talked about space complexity, we discussed different examples, and we also discussed that auxiliary space is a better criteria to compare to algorithms, especially the algorithms which are using an input array or list or set of size n.